So far, the history of materials science in the military has been an arms race. Better weapons, better armor. Better weapons, better armor. But at least in man-made materials, we may be approaching a limit. Here at MIT, researchers are studying inspiration for the next level by analyzing a much older arms race, one that's been going on for hundreds of millions of years. I refer, of course, to the one that's been going on in nature, under the sea. One great thing about high-speed photography is that it lets researchers study exactly how materials break when they're under stress. It turns out that man-made materials tend to break catastrophically and suddenly. Here at MIT, they've discovered that materials in nature often fracture more gracefully. The thought is, if we can study that, maybe it'll lead to better protection for ourselves. One really cool thing about high-speed photography is that it lets you see exactly how materials fail when they're under stress. And it turns out that man-made materials often fail rather catastrophically and abruptly. That's definitely how I fail when I'm under stress. But here at MIT, they're studying how materials in nature often fail more gracefully. The thought is, if we could figure out how nature pulls that off, maybe we can replicate that and make materials of our own that are a little safer and a little better. Can I intrude?
Sure, hi.
David.
Christine Ortiz, nice to meet you.
Too. Oh, you have a serf here, an indentured servant. David.
That's
nice.
Graduate student Matt Connors.
Nice to meet you. All right.
So what are you doing here? You got a box of something?
So we've just received a delivery of live mollusks. Hopefully they're live from an aquarium in California.
Live mollusks?
Yes.
By UPS?
Yes.
You couldn't order a pizza like a normal college kid? Is it going to be like on dry ice? Like it's going to be packed like sushi?
These actually live in a low temperature, low 40s. So
The longer
anything
we
they keep that
stand here
temperature.
talking,
Yeah.
the warmer they're getting.
Yes,
Maybe
yes.
we should open
So
it.
that's why we have an aquarium with a chiller
Yeah.
that chills down to the temperatures that they're used to in their environment.
When you say mollusks, I mean, isn't that just a whole category? Isn't
Yeah.
this a particular...
This is a particular species of mollusk. It's actually called a chitin, and it's the largest of the chitins, and so it's called a gumboot chitin.
Wow.
It's very unique because it has a very thick, kind of fleshy. You know, typically they look like giant worms.
Cool.
So well see what they look like.
worms, yeah.
It's called a chitin?
Chitin.
I think
yeah.
there was a movie about these, Clash of the Chitins. No? All right, let's take a look. Let's see what's in there. Wow.
I guess this is some algae. Back to
Right.
there, it's ice.
Right.
You got a bonus pack of algae?
I'm not sure if it's algae, right? Yeah, we'll see.
May I?
Yes,
Sure.
I mean, I'm not in the union.
Sorry.
So these are chitins?
They're in there somewhere.
They're in there somewhere. In
Yeah, we have to take. There's a lot of stuff.
algae
that
and foam. Yeah.
Here's your
Right.
seafood banquet right there.
Let me help you out.
Okay.
Yeah.
Wow, it is huge.
Yeah, it feels really weird.
Science as it happens, folks. Man,
Wow.
right out of Aliens.
Yeah. So this is underside.
Uh-huh.
And it's alive?
But it's alive right now.
Survived the air travel?
It did. It's a little
Okay.
sluggish right now.
I
Yeah.
don't blame
This
it.
is the other side. This is its.
And so one of its mechanisms of protection is to curl up into a ball. So these mollusks can adhere to substrates, and when they're dislodged, they can curl up into a ball. And so you see, this is like, it has this very fleshy kind of tissue on the out part that's covering the internal exoskeleton. And so there's multiple plates inside that enable this articulation of it moving into a ball.
Wait, you said an internal exoskeleton?
Well, it's an exoskeletal plate because it doesn't have any bones in it. But this is a very unique system which has tissue, a thick tissue, or a polymer layer on top of those plates.
Wow.
Yeah.
And how strongly is it curling?
It's curling very strongly. Yeah. Very
Wow.
interesting.
Yeah, I think we should. It's
probably
probably
put it back
yeah,
in.
dehydrating. Can we give it some water?
And so why did you order these guys?
So we're interested in a number of things about these animals. First of all, we're interested in the exoskeletal plates. So they have 8 exoskeletal plates inside, and it enables them some mobility. So they're very different from typical mollusks, which have a single kind of seashell. So these are unique in the sense that they articulate and they have a flexibility to it. So they adhere to substrates, rocks, and when a predator attacks, if they're dislodged, they can roll up into a ball and protect themselves. And so we're interested both in the calcified plates that are inside, as well as the fleshy kind of tissue on the outside, which is also very unique. Most mollusks have a very thin polymeric layer on the outside.
What are some other mollusks that people might know?
Abalone, red abalone, trochus, all kind of seashells are typically mollusks.
Okay.
It's not actually a complete circular spherical paw. If you look at it, it's actually there's some asymmetry to the animal, and that's what we're actually really interested in. And you know, how do these plates actually articulate? Because there must be some polymer between them that allows the movement, right? And so
Right.
you know, it's an armor. It's a flexible armor, but it's still rigid. And so, you know, how do you get this movement? I mean, you could imagine, you know, using this for flexible joints, all kinds of different things.
But is it that different from like a person's spine or like the overlapping things on a lobster shell?
Very different. So they're actually, depending on the different types of armor, there's completely different interlocking mechanisms. So the fish, our armored fish, actually has a peg and socket joint. These actually have sliding plates that go next to each other. There are others that have hinges. So there's a whole different array of interlocking mechanisms for armor. And so we're interested in understanding how does that give you these flexible, you know, mechanisms. It's really amazing.
Little guy. Oh man.
Yeah, so he seems like he's starting to curl.
You're right. So it's cold and it's wet and it's slimy, and this is flesh, right? It's not meant to be hard. It's hard, but it's soft hard.
There's an external flesh, softer flesh over the exoskeletal plates.
Right.
Yeah.
So how do they move? There are no features for.
Right. So, you know, that's one of the things we're going to be looking at. They adhere, and then, well, sea urchins have little plates that can move it along. I think probably it just moves, you know, just generally like a worm, but we'll see. We'll watch it and see. So there are many animals which are living fossils, and that means that they've changed very little over the many millions of years of evolution. And so, you know, for example, our armored fish is actually, the plates in it are almost the same exact structure as 500 million years ago. There are many animals that have evolved in terms of its plate-like structure. And so what's happened to many animals is that they've lost their armor, they become faster, and then they came out of the ocean like us. And so they've opted for mobility over protection.
But this guy.
And this guy is there were many animals that looked similar to this guy many years ago.
So I might have seen something looking just like this millions of years ago?
Maybe.
Wow.